Hi there, and welcome to Steam It with Steve. Today we're going to go through something I'm super passionate about as a computer scientist, how the binary number system works. So today, basically, we're going to learn how to count in binary, which goes something like this: 0, 1, 10, 11, 100, 101, 110, 111, 1000. Now, I'm not crazy. This system is super important for computer scientists, and hopefully by the end of this video, you'll agree with me as well. So to begin with, I'm just going to show you a little PowerPoint that I've put together for you, which is going to go through all this content in a happy, reasonable way. Right, so number systems with binary. So first of all, how do we actually count with our normal number system? So let's think about that for a while. So to start, we usually start with 0. Then we go 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? And that's the same system that we've been learning since preschool. To build on that then, once we get to 9, do you see we've used every single character we can use in our system? And then what we do is we merge that with the next number we have. So we go into the tens column. And then we go 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Right? Now, if we look at that carefully, do you see how the pattern of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 has happened again, but all we've done is we've jammed a 1 on the front. Right? Then if we go to the next system with 20s, you should see that the same pattern is happening, but instead this time, a 2 has been placed on the front. Then when the 3 happens again, same with the 4, but the same core numbers have been used over and over. So what happens here is basically we use the same pattern of 0 to 9, and then we put on another column. Now this will happen all the way through. So 70s will happen all the same with the 80s, and then we'll get to the 90s column, where it'll go 95, 96, 97, 98, 99, and then we go to the next column, which means that we start again with this pattern. This is how our modern number system works, which is quite interesting. And the purpose of today is we're going to look at a few other number systems, which hopefully give you some more ideas of how they work. And then that will allow us to build our binary system. Okay. So I want you to imagine now, instead of being able to use the 2, the 3, the 4, the 5, the 6, and the 7, and 8, 9 characters, so these symbols, you can only use the zeros and ones. Okay, so if we read through this, we can use that, we can use that. We can't use any of these if we were to use only zeros and ones. But we can use this, right? And that's what we're going to focus on today. So I want you to think about a new number system. So I want you to create a new number system, not using the same characters that we have always used, but you're only limited to using 0 and 1. And I want you to create a number system all the way from 0 to 5. Okay, so just using zeros and ones, how could you make a new number system like that? So please pause the video now, have a go over by yourselves. Okay, so there should be 6 different characters, and we'll come back. Hope you've done it. Okay, awesome. So what I'm going to do is show you this little spreadsheet that I built. So here's all the numbers down here. Now let's think about this. If we put in the next number, right? So if we do all the single digit characters, they're the same, right? 0 and 1 is 0 and 1 is 0, 1 in decimal, right? Let's say that we went to the next column and we can't use a 2, we can't use a 3, but we could use a 0 or a 1, right? If I put a 0 there, that limits me, isn't it? Yeah, because that is the same as this one, right? So the only other characters we can use is 1. So I could potentially do that. And then the only other combination that is left is that, right? But do you see how this isn't in order? So you're going 0, 1, 11, then back to 10. That's a bit awkward, right? So what we do in our normal binary system is we actually go 0, 1, can't do 2, 3, 4, 5, 6, 7, 8, 9, but we can do 10, right? So we've used the 10, and then we can use 11. So basically, 2 is 10 in binary, which is the way that a computer understands. Now, the cool part with this is once you've done this pattern, you should start seeing that it repeats itself. So see how it's gone 0, 1, 0, 1, 0, 1, just like that first column with the 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we went 11, 12, 10, 10, 11, 12 with the 2s all the way through. This pattern actually repeats all the way down. So if I do this, and then I jam 0s on the front of the first ones, because they haven't changed, but now I put 1s, this is actually how the number system in binary works. So 0, 0 is 0, 0, 1, sorry, 0, 0, 1 is 1, 0, 1, 0 is 2, 11 is 3, and then when we get up to that, we can't use any of these characters anymore. We can't use 20, can't use 30, 40, all the way up to 90, 96, 97, 98, 99, but we can use 100. How cool is that? Right? And then that pattern goes on and on and on. So if I want to repeat the next set of numbers, all I do down here is go copy, paste, and I'll put 0s on the front of all these ones. And this is how beautiful the pattern is. You should start seeing the rectangles inside the rectangles. Oh, not that. Yeah. So what you should start seeing is it's doubling each time. So 1 was there. 2 was in that column. See how 4 was the next column across? So when it's 1, it's just 1. When it's 10, that's a 1 in the 2's column. This is the 1 in the 4's column. And then look down here, there's a 1 in the 4th column across, which is the 8's column. Right? And you see this is the same as 8 plus the 1, which gives you 9. If you come back here, the 3 is the same as 2 plus 1. The 4 is the same there, but then 5 is the same as 4 plus the 1. How cool is that? There's a little pattern there. So if we want to go to the 16s, what actually happens is that. Right? And then if we want to keep going, we basically keep repeating the pattern. So we go 1, 0, 0, 0, 1. And that would be 17. Whoop. Whoop. Okay. So that's just, we're going to go into a bit more depth on that, but that's, hopefully you built some system up to 5 that looks like something like this. So 0, 1, 10, 11, 100, and then 101. Okay, so if we go back, powers of 2 is super important in binary, right? Which hopefully you've picked up on. So 2 to the power of 0, so anything to the power of 0 is just equal to 1. 2 to the power of 1, so 1 lot of 2 is 2. 2 times 2 is 4, or 2 squared is 4. 2 times 2 times 2, or 2 to the power of 3 is 8. 2 to the power of 4 is 16. 2 to the power of 5, 32. 2 to the power of 6, 64. 2 to the power of 7, 128. 2 to the power of 8, 256. And then 2 to the power of 9, 512. And then 2 to the power of 10, if you did do it, was 1024. These should look familiar if you've done any gaming, right? So graphics cards love using these numbers in terms of how many gigabyte that they throw at it. And then you can also look at the megabytes that are thrown into it. So some graphics cards might have 512 mega RAM built into it, which is quite common. Or the Nintendo 64 you might have heard of before. These were all numbers that were built on that. These numbers are sacred to computer scientists. They are the building blocks of our number system, which is the binary number system. Okay, a computer can only understand 1 and 0, which hopefully by the end of this you will as well. Okay, so we're just going to go on a bit of a tangent here. So deviating away from the 1s and 0s, we're going to go look at number systems that we should have all seen along the way, or some we might not quite have, but we'll get to see the patterns and understand the difference. So what is the difference then between a character and then a number? That's what we need to think about. So if I said the number 3, what does that mean? Does it mean 3 fish, 3 PlayStations, 3 fingers? We can do it when we give a concrete example attached to it, okay? But that's the numeric value, but there's characters or symbols that we use to show it. So in our normal number system, we do it like that, right? The ancient Romans would have done it like that. We can rewrite it as a word, so we could say 3 in characters. We could do it like the Chinese or Japanese with the 3 slashes on top of each other. The Mayans did it with 3 dots, or we could write it as an improper fraction. All of these mean exactly the same thing, but they're represented differently. Okay. And that's what we needed to get to. So basically, a computer can only understand certain things, and we need to be able to write it in the language that it can understand. So all these characters have the same meaning of 3, but they describe 3 in different ways. Okay? Characters are simply symbols that humans have attached a meaning to it. Okay? They don't necessarily mean anything apart from the meaning that we put onto it that's come from the generations before us. So a number is an abstract concept, just to mess with your head. I can't show you 3. I can show you 3 things, or 3 pizzas, or objects, but I can't show you the concept of what 3 is. Okay? And that's what we need to understand when we're looking at this. So when we look at Roman numerals, which is something that you should have done back in the day in junior school, we had this number system that we worked with. So I was equal to 1, V was equal to 5, X was equal to 10, L represented 50, C or century represented 100, D represented 500, and M for millennium, maybe 1000, right? So you might remember your centi in millimeters. That's where it actually comes from. So when we look at it, I was 1, I was 2, I was 3, IV, so instead of 4 I's, they reduced it down to 2 characters. So 1 before 5 was 4, V was 5, VI was 6, VII was 7, VII was 8, 1 before 10 was 9, and then X was 10. So if you look at the number system, they actually have these midway points of 5 because of the 5 fingers on our hand. And they would know whether or not they were 1 before 5 or if they had a group of 5 and then the next set above it. How cool is that? Okay. That pattern would repeat between the groups. So V and X would be linked, L and C would be linked, and then D and M would be linked. Okay. C and D was also linked, sorry, as well. Because you could say 100 before 500. Okay, so then if we wanted to represent 11, we would just go XI, XII, XII, XIV, and so on. What you should see is this pattern of I has repeated itself all the way down here as well. All we've done is jammed on the front an X, haven't we? Okay, that would then repeat as well. So once we got to 20 and kept going, instead of just 1X, which we've done with the tens column, you would write XX, and so on. All the way up to 30, which was 3 X's. So then if you want 40, you would do XL, 50 was just L, LX was 60, and so on. Okay, and then that was sort of the pattern. What you see though is a pattern, and that's the cool part. And it's a little bit more complex, but with our binary system, hopefully you've seen that it's a pretty simple pattern because all you got to do is put 0 and 1, and then just split it out like a branch each time that you go through. So next challenge, I'd like you to just to pause the video there and have a go at this. So convert the following numbers to decimal. So have a go, pause it, and I'll talk to you soon. Hopefully you paused it. Okay, great. So convert the following decimal numbers. XI is the same as 10 and 1. So you can either cheat just by reading it off on this table, or you could look at it and go 10 plus 1, oh, that was 11. Okay, the next one was then XXIII, which is the same as 23. So XL is 50, IV is, XL is 40, and IV is 4, so then that makes 44. LXX is 70, VII is 8, so then that makes 78. XCIX makes 99. Then if we convert the following Roman numerals going the other way around, we've got 8, so that's between V and X. So 8 is 3 after 5, so it's VIII. 42 is 1 before 10 before 50, so that's 42. So 40 is XL, and then 2 is II, so XL, II combined together. 73 is LXX, and then 3 is II, so LXXIII. And then 89 is LXXX, and then 1 before 10, so IX. Then we've got 475, just to be a bit of a madman. So if we come down here, we've got C and D. So it's 100 before 500, so it would be CD. 70 was LXX, and 5 was V. So then combining that all together would be CD, LXX, V. How cool is that? So the whole point of this though is these are just symbols, but they mean exactly the same thing. And that's all that we've done is we've had this table here to convert between the two. So just as a bit of a history lesson on the different number systems on top of that one. So the first one way back in the day is the ancient Egyptian numbers, where they actually use hieroglyphics or little characters to represent different numbers. So for example, a candle represented 10,000, or a whip represented 100, a staff was 1,000, it looks like a bird was 100,000, and then the pharaoh was worth 1,000,000. The really cool thing about this system is they even included fractions, so they understood what a half, 2/3, and so on were, using this symbols through here, which I thought was quite neat when I was looking through. The next system that was developed was the Mayan number system, which a little bit easier to read because it was just based on dots. So you would put 1 dot, 2 dots, 3 dots, 4 dots. And then when you got to fifth, you would just draw a line through the dots and then continue on the top and then put the dots above it. The thing that was unique about this system, though, was they were the first to discover the zero. So the zero looks like the little football here. And basically that was quite unique because before then, no one had actually quantified it in a numeric symbol. So that's what the zero would be represented. And it's quite interesting how that's actually followed through to our modern number system as well. It's just got a few more complicated things inside of it. The Chinese number system then was another one. And it's interesting how these all developed externally away from each other and then they've sort of come together. So the Chinese number system basically was a series of dashes. And then when you got to past 3, the 4 would look a little bit more complicated. I'm not quite sure on the history behind this, but it looks very similar to our decimal system as well because they've gone 1, 2, 3, 4, 5, 6, 7, 8, 9. And then they do groups of tens, hundreds, thousands, 10,000s, and 100 millions. Similar is to how the Roman numerals sort of worked by merging them together. They also had the zero as well, which was pretty cool. And the way that they draw the zero looks something like that, which I thought was really neat. The other new number system that I found, which was really unique, was this one, the Sister-Cian digital scoring system. And basically it's one character that represents numbers all the way from 1 up to 9,999, which is pretty cool. And the way the number system works is based off quadrants. So in the top right corner, you would that would represent the first digit or the ones column. The next top left column represents the tens column. The bottom right hand corner represents the hundreds column, and the bottom left, represents the thousands column. Now, if you look at it carefully, they actually use exactly the same character in each of these columns. So, for example, the 3 was a hook, but just whatever quadrant or corner that it was in, has a different has the same symbol, but it's placed in that quadrant. So if we look at the number 4,723, the 4,000 is this corner here, so the straight line, which is there. The 700 is up here, which is the open square, so the square with a little roof on it. The 2 for the 20 was here, so that's in the top left, and the 3 was up here for going down. So when you read this number, you actually go from this corner here and then around like so, which is pretty cool. But again, it's just a symbol, but it represents exactly the same thing as these numbers above it. And that's all we need to get into our mind is there's many different ways of writing a number that isn't just using our normal 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So the history of our modern number system actually is derived from Brahmi, right? So from India. So it started off looking something like that, went to Hindu, then Arabic, then the medieval system, and then came to our modern number system. So the Brahmi system used single dashes like this, and then merged them together. Then the Hindu system basically rotated it around, and then the Arabic system cleaned it up, so just slightly changed it. So some of the 2s and the 3s obviously rotated around. Then the medieval was the next one, which looks a little bit more familiar. So that 1 looks like an eye. The 4 looks like a fish upside down. 5 for the 5, and the 7 looks a little bit squashed. But these were all the systems of the numbers that were built, which is pretty cool. So how many characters are there in our modern number system? Well, there's 10. So we've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? So our modern system, you might be asking, why do we count it into groups of 10? And the answer to that is actually right in front of your face. Okay. Have a think about it. So the reason is actually because humans have 10 fingers. Okay, so we have 10 fingers. So the way we count is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So one group of 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So I have 100 groups. So 10 groups of 10, which is kind of cool. And that's how our modern number system is built on. So modern numbers look something like that. And you should see the pattern where it starts from the first column and just repeats by using the columns in front. So technically we could rewrite that as 0 on the front of all these as well, just to get your head in the game if we were to had to write 2-digit numbers. So how our number system works, if we have 49,140, this would be the ones column. This column here is then the tens column, followed by the hundreds, then the thousands, and lastly the 10,000s. So up here we have the 10 to the power of 0. This is the same as 10 to the power of 1, 10 to the power of 2, or 10 times 10, 10 to the power of 3, and the last column is 10 to the power of 4. Now the way that we interpret this is the same as this, and it might seem a bit weird, but this will make more sense when we get to binary. This is the 0 times 1 column, so that gives you 0. Then 4 times 10, which gives you 40. Then 1 times 100, which gives us 100. 9 times 1,000, which gives us 9,000. And lastly, 4 times 10,000, which gives us 40,000. Notice how they're all in groups of 10. So the base of these powers is all at the base 10, which is going to be useful when we get there. Okay. So what does base 10 mean? Basically, it's the decimal number system. So base 10 is the number system that you guys have used already. So a number is formed using the groups of 10, and it's using these same characters again. So for example, 3,267 is 3 lots of 1,000, 2 lots of 100, 6 lots of 10, and 7 lots of 1. So this is also sometimes known as a denary system. Okay, so what characters can a computer understand? So 0 and 1 is it. So it only understands true or false. And we represent this mathematically with either a 0 or 1. And this is what our binary number system is built on. So it only understands this. Now, just to add a bit of terminology in here, it's also known as base 2. So when we look at a computer, it understands base 2 systems. It doesn't know what the character of 3 looks like. It can only ever understand if a light switch is on or off. And there's a series of these switches all in a row that makes up the number. Okay. So when we look at decimal versus binary usable characters, 10 has all of those, whereas binary only has the 0 and 1 to build on. Okay, which hopefully we'll see as we build this pattern. So how do we count to 3 in binary? Let's have another go at this. So hopefully we've had a little bit of time, let that marinate in us, and we can think about this a bit more. So the only usable characters in base 10 is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Whereas in binary, we can use 0 or 1. So in decimal, we can go 0, 1, 2, 3. That's the same. So counting to 3 is the same as what we've done before. So if we look at the grid, we can use binary would use exactly the same again as wouldn't it? Because 0 is 0. We can use that. Can we use the 1? Absolutely. We can just use the 1. So the first two characters in decimal and binary, exactly the same. When we look at the 2, we can't use that because the only usable characters are 0 and 1. So we can't use the 2, we can't use the 3, the 4, the 5, the 6, the 7, the 8, or the 9. But when we get to the 10, we can use that because 1, 0 is valid, 0 and 1. So the computer could understand a switch being on and a switch being off. So 10 is actually equal to 2. We can then use 3, which is then a 2 has happened and then a 1 has happened. Do you see how they merge together to make a 3? So this 11 means that there's 2 plus a 1, which is 3. If we think about the groupings that are happening here. So the first group is you can either have 0 or 1, right? And then the next column is basically your 2's column because you've got a 2. Yeah, absolutely. I've got a 2 and no 1. That's what that reads. I read this one. It means I have a 2 and a 1, which merge together to make a 3. Okay. So here's a bit of a dad joke, which is a bit funny for me, but haha. So there are 10 different types of people in the world. Those who understand binary and those who don't. Okay, let that sit and marinate. If you haven't gotten it, basically it means because the 10 is 2. So 2 types of people is the same as 10 in binary. Okay. So how do we count to 5 in binary? Right. So it's the same as this. These are the usable characters in decimal, and then these are the usable characters in binary. So if we go 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, we can use them again. We get to 10. So that means I've got 1, 0. So I've got a 2, but I've got no 1. Then I can use a 1, 1, which means that I have a 2 and a 1, which makes a 3. Then we get to 4. So we can't use 12 because that's got a 2 in it. That's illegal. We can only use 0s and 1s. So we can't use the 12, the 13, the 14, the 15, the 16, 17, 18, 19. We could use the 0 in this number because that's legal, but we can't use the 2. So then all these, because I've got 2s on the front of them, can't be used. So the 20, 21, 22, 23, 24, 25, 26, 29. Then the 30, yes, we could use the 0, but again, we can't use the 3. So all the numbers, because they've got these characters on the front of them, are illegal. We can't use any of the 4s. We can't use any of the 5s. The 6s won't work. The 7s won't work. The 8s won't work. The 9s won't work. So 90 all the way down, 97, 98, 99. But then we can use this one because this has legal characters. It can use a 0 and a 1. So we can use 100. Which basically means that we have one lot of 4, no lots of 2, no lots of 1. Right, then we go to the next column. So 1, 0, 1 means that I can do it because I've got a 4, I don't have a 2, which was this, and I do have a 1, which merges together to gives you back to 5, which is kind of cool. Hopefully you're picking up on the pattern there. So then if we want to go a little bit more complicated, let's say we want to count to 10. So I'm doing this a couple of times just to practice counting, right? So I don't know if when you're a child and you see them the first time, it's like 0, 1, 2, 3, 4. Oh, what's the next one? 5. Oh, what's the next one? 6, etc. This is so much easier because you only have 2 characters to work with. You only have a 0 and a 1, and it just builds on it from there. So if we're trying to build this, the usable characters for decimal is 0 to 9. Whereas the usable characters for binary is just 0 and 1. So we can do all those. Binary is exactly the same, so 0 and 1 stays the same. The 2 we worked out was 10. 3 was 11. 4 was 400, was none of these ones, so we can't use all the way up to 96, 97, 98, 99, and then 100 we can use. 5 was 101. 6, we can't use 104, 105, 106, 107, 108, 109, but we can use 110. Now, if we look at that, that's the same as saying we've got a 4, because we've got one there, and we have a 2. So 4 plus 2, that actually equals 6. Then we can go to 7, which is 111. That does work, doesn't it? So we can put that there. So that means we have a 4, a 2, and a 1. So 4 plus 2 is 6, 6 plus 1 equals 7. So that actually works. We can't then use all these characters because they've got 2, 3, 4, 5, 6, 7, 8, 9 in them. So I can only use 0 and 1. The same pattern will happen again. We can't use any of these numbers. Can't use the 200s, the 300s, the 400s, the 500s, 600s, 700s, 800s, 900s. Can't use them. But what we can do, the very next one is, after this, it's like going 98, 99, 1000, right? Does everyone see that? So then that's literally how that builds up. Now this means that there's a 1 in the 8s column, no 4s, no 2s, and no 1s. So we have 8. So a 9 would be the same as an 8 plus a 1. That's why it's a 1, 0, 0, 1. A 10, if you think of it, would still have an 8 and then would merge it with a 2, wouldn't we? So we would have 1010. And if you look at this pattern, see how it's going 0, 1, 10, 11, 0, 1, 10, 11, 0, 1, 10, 11. So if we wanted to get 11, it's actually 1, 0, 1, 1, which would be an 8 plus a 2 plus a 1, which is kind of cool. So hopefully that's helped to get your head around a little bit more on the pattern. Sorry, my head's just been in the way. So you could have seen that. There we go. So how the binary system works. If we look at it, instead of having the 1s, the 10s, the 100s, the 1000s, the 10,000s, what we have here is instead we have the 1s column, then the 2s column, then the 4s, then the 8s, then the 16s. That's why I said those numbers were sacred for computer scientists. If you know these numbers back to front, it's going to save you a whole heap of time down the track. Now, the cool part, if it's got a 0, means that it doesn't have anything. If it's got a 1, it means it's got one of those. So when you work out this number, it's actually quite easy as long as you know these columns. You just literally add them up. Okay? So another way of thinking about it, remember how we talked about the bases? So our decimal number system was base 10. When we deal with the binary system, it's actually base 2. So when we see this, it's 2 to the power of 0 instead of 10 to the power of 0. But anything to the power of 0 is actually equal to 1. This column then is 2 to the power of 1, 2 to the power of 2, or 2 times 2 is 4, 2 to the power of 3, or 2 times 2 times 2, and the last one's 2 to the power of 4, or 2 times 2 times 2 times 2, or 16. So if we look at it, that means I have one lot of 1, no lots of 2, 0 lots of 4, 1 lot of 8, and 1 lot of 16, which then adds together and then gives us 25. How cool is that? So 25 in our decimal number system is the same as 11001 in the binary system. How cool is that? So now we have a way that a computer can understand our numbers, because they understand what on and off is, which is what this number system does. Hopefully that helps. Cool. So if we made up a grid of all the numbers, the significant numbers for us are powers of 2. So 0, 2, 4, 8, 16, 32, and 64, which we'll have a look and see what happens. So if we do the first one, that should be easy. 0 will be there, then 1, then 10, 11, 100, 101, 110, 111, 1000, and then 1001. So you should see the 1, 10, 11, 1, 10, 0, 1, 10, 11, 0, 1, 10, 11, 0, 1. Guess what's going to happen here? 1, 0, 1, 0. Right, so the pattern just grows on itself. So this gives us 1, 0, 1, 0, all the way up to 16. And that's what I meant by this power of 2. So see how they've had to add in another column because we've filled it all up. We've done 4 individual numbers or 4 places in the number, and then we've run out of space, and then we've had to add in the next one. And if you look here at our power of 2, see how it's grown? It's gone from 1 digit to 2 digits. The 4 went up another from 2 to 3 digits. The 8 went from 3 digits to 4 digits, or 2 to the power of 4, which is 8, 2 to the power of 5, which is 16. See how that's 5 digits across? And then that pattern will go on forever, right? And that's literally how a computer will count. It will keep going and growing. And see how when it gets to 32, there was 5 decimal places, and now it's got the 6th decimal place. And then it starts all over again. It goes from 1, 10, 11, 100, 101, 110, 111. So then the next one will be, what, 101,000. And then 100,000, 1, 10, 11, and then it just keeps going and growing. So you should see that it goes 0, 1, 0, 1, 0, 1, 0, 1 for the first column. Then it goes 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0 for the second column, because there's 2. Then the third column will go 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0. Then the next one will go 1, 1, 1, 1, 8 times, 0, 0, 0, 0, 8 times. And then the next one will go 16 times with 1s, and then 16 times with 0s, and then 16 times with 1s. Hopefully that's giving you some insight on how the number system sort of works. So basically you just need to think about what column are you currently in, and then how does that work? So base notation basically looks something like this. So if you have the decimal number 12, if we want to say that it's definitely in base 10, it's kind of like chemistry. You write a little symbol to the right down here. Okay, so if we write that in binary, it's 1100. So I have an 8 and a 4. So 8 plus 4 is 12. So the decimal one, we write a little 10, which means base 10. And then the binary, we write a little 2 next to it, which means base 2. Okay, so this is where base 2 sort of lies. Now, this small number in the bottom right-hand side describes the base. So please don't do this in your math exams, because your teachers will get probably annoyed with me. Okay, so that's what the base means in the corner there. Okay, so I'd like for you to have a little go at this challenge. Okay, so I'm going to give you a whole heap of numbers. So 1, 2, 4, 8, 16, 32. So I'm giving you the powers of 2. please use this grid if you need it to convert this number based in here. Okay, so I'll show you the first one just to get your head around it. So 11, if I put there, means I have a 2 and a 1. So it means 2 plus 1. 11 in base 2 is the same as 2 times 1 plus 1 times 1, which is the same as 3 in base 10. Okay, which should make sense, because if you count in binary, we go 0, 1, 10, 11. Okay. The next one, have a go. Pause the video there, see if you can do them all, and I'll see you soon. Awesome. So coming back, here we go. So we go 1, 0, 1. So we have a 4, then a 1. So that means we have one lot of 4, no lots of 2, and a 1, which gives us 5. We then go to C. So we have 1, 0, 0, 1. So it means we have an 8 and then a 1, which adds together to give us 9. The next one, then we have an 8 and a 4. So we have one lot of 8, one lot of 4, no 2s, no 1s, which adds together to give us 12. 1, 0, 0, 1, 0 means we have one lot of 16, no 8s, no 4s, a 2, and then a 1. So we add that together. That represents what 18 is. And see how the numbers are getting bigger? Because once you got past 8, would be 4 digits, right? Once you get past, what, 15 would then become 16 digits, and 5 digits, and then so on. So this one then, 1, 1, 0, 0, 1. So we got a 1 there, a 0, a 0, a 1, a 1, a 1. So we're up to the 32s. So we have one lot of 32, one lot of 16, one lot of 8, no 4s, no 2s, and a 1, which gives us 57. Then we go to the next one. So 1, 0, 0, 1, 0, 1, 0, 1, 1. So we've got one lot of, I'm going to cheat a little bit here. So this is the 256 columns, because we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're up to there. So everyone see that? So 1, 2, 3, 4, 5, 6, 7, 8, 9. So 256. We don't have the 128s. We don't have the 64s. We've got the 32s. We've got no 16s. We have an 8. We've got no 4s. We've got a 2. And then we have a 1, which adds together to give you 299. Awesome. Hopefully that's made some sense, and you now can be able to convert from binary into decimal. We will go through next time how to go the other way around. It's not that hard, but I wanted to leave it there and just move on to a little Kahoot. So there's the Kahoot. Open that one up. We'll try and do it in class and have a bit of fun with it. If not, just click on that link and have a go yourselves. Thank you very much. Hope you've enjoyed. See you next time.